Last time we discovered that phasors of currents and voltages satisfy the network equations, namely KCL and KVL, respectively. In this hour, we will try to figure out what do terminal equations imply on phasors of currents and voltages. We begin by the simplest case, namely an LTI resistor. Okay, suppose that we have a resistor somewhere in a circuit with resistance R, and that circuit is in sinusoidal steady state. Therefore, this component is part of a circuit that's in sinusoidal steady state. This is its voltage, VRT, and this is the current of our LTI resistor, whose resistance is R. And this belongs to a circuit, an LTI circuit, in sinusoidal steady state at the operating frequency of omega radians per second. Okay, so that means VRT, the voltage, is a sinusoidal signal oscillating at frequency omega radians per second. Okay, therefore, this can be written as the phasor of the voltage times e to the j omega t, and then you take the real part. So this was our relation between the time domain signal and its phasor. Okay, and IRT is the real part of the phasor of this signal, IR, times e to the j omega t, and then you take the real part. Okay, so for instance, if VR is in polar form, has this representation, okay, the magnitude times e to the j phi. In other words, if this is phi and here the magnitude is a, and this is r, suppose VR, so that means that VR of t, remember from the previous lecture, this time domain signal reads something, some sinusoidal with some magnitude, okay, and with some phase. The magnitude of that sinusoidal is a, because that's the magnitude of this phasor, that complex number, and the phase of that sinusoidal is the phase of that complex number phi. As for the frequency, that's the operating frequency, and it's determined by the input or inputs that are driving the circuit. Okay, so this is the voltage, this is the current, and this is the relation between their phasors and themselves. So VR is the phasor of VRT, and IR is called the phasor of the current, IRT. Okay, now what we know is that this is an LTI resistor, therefore the voltage and current should satisfy Ohm's law. In other words, VR of t equals R times IR of t. And now what we're gonna figure out is that Ohm's law, that relation, or what that relation implies on the phasors of voltage and current. And it's very simple to obtain. All we have to do is take these expressions and apply to them the constraint, which is Ohm's law. So, what's the relation between the phasors of voltage and current of an LTI resistor? Okay, we begin from Ohm's law. Okay, voltage equals resistance times the current. And then what we do, we write the voltage and current using this representation. So that means real part of VR e to the j omega t equals R times the real part of IR e to the j omega t. Okay. Now R is a real number, therefore we can take it inside the parentheses and write this equals R IR times e to the j omega t. Okay. Now remember from the previous lecture some of the identities that we have listed. Okay. And one of those identities was the following. Suppose that you have two complex numbers, x1 and x2, and then you multiply both with e to the j omega t. Okay. And then if their real parts are equal for all times t, then it must be that x1 equals x2. And that property immediately gives us the relation between phasor of the voltage and phasor of the current for an LTI resistor. Okay. What we have is VR equals R times IR. Therefore, the Ohm's law in time domain is directly carried by form into the so-called phasor domain. And we obtain this relation, which is very easy to remember because it's same as the Ohm's law. Its form is same as the Ohm's law. Okay. Now let's represent VR and IR through their phasor diagrams. Okay, so phasor diagram. This is the complex plane, real axis, imaginary axis, origin. And suppose that this is the phasor of the voltage VR. Okay. Now this says that for a passive resistor, that is the resistance is positive, this says that IR should be a scaled version of VR. In other words, IR should be somewhere on that half line. Let's say it's here. Okay. The ratio of their magnitudes depends on the resistance, but as for the phase, both have or must have the same phase. Okay, so both VR and IR, the current, the voltage and current phasors, have the same phase. Okay, let's say phi. Such signals are said to be, that is, signals which have the same phase are said to be in phase. Okay, so for an LTI resistor, therefore, the current and the voltage are always in phase, regardless of the resistance. Okay, now let's move on to more interesting components, namely inductor and capacitor. Again, our aim is to figure out the relation between the voltage phasor and current phasor for inductor and also for capacitor. Now let's begin with inductor. Okay, this is our inductor. It's part of a circuit, an LTI circuit that's in sinusoidal steady state. This is the voltage, the current, and L indicates the inductance of our inductor. Okay, so this guy has the phasor, capital V of L. This guy has the phasor, capital I of L. And the relation between the time domain signal and its phasor is simply VL e to the j omega t. And IL t is the real part of IL e to the j omega t. Omega is the frequency of operation, okay, determined by the input in the circuit. Okay, so to figure out the relation between voltage and current, what we're going to do is we're going to take these expressions and apply on them the constraint, which is the terminal equation, okay, to be satisfied by the voltage and current of the inductor. So what we have therefore is VL of t equals L d IL t. Okay, so that's our terminal equation in time domain. So let's rewrite VL and IL through these expressions. So what we have is real part of VL e to the j omega t equals L d times real IL e to the j omega t. Okay, so what we know is, first of all, L is a constant, a real constant, therefore we can place it anywhere we like, and we can directly carry it inside the parentheses. And also from our previous lecture we know that this is an operator, derivative operator, this is a real operator, and those two operators commute, meaning that we can carry this derivative operator inside the brackets. So let's do that. What we have is the real of L, IL, and then derivative operator e to the j omega t. Okay. Now, e to the j omega t is a function of time. It's very easy to take its derivative. You just multiply the thing by j omega. So if you do that, or by doing that, we can get rid of this d operator. And we have j omega, this term coming from differentiation, then L times IL times e to the j omega t. Okay. And now all of a sudden this differential equation turned into an algebraic equation. Again, we have the same situation here, something multiplied by ej omega t, and here we have something else multiplied by ej omega t, and those two complex numbers, they have always the same real part for all times, and that's only possible. This equals that. Likewise, if this equality holds for all times, which it does because terminal equation holds at all times, it must be that this voltage or phasor of voltage must equal phasor of current that's being multiplied by that complex number j omega L. So let's write our finding here, j omega L times IL. Okay, so what we obtained is quite remarkable. The relation between voltage and current is described by a differential equation in time domain, but if you look at the thing from the phasor point of view, the relation is algebraic, and we know that algebraic equations are much easier to deal with differential equations. And how about the phasor diagram for the voltage and current of the inductor? Okay. Suppose this is our complex plane, real, imaginary. And suppose that we're dealing with a passive inductor. L is positive. Okay. So, and this, let us represent our current phasor, IL. Now, if that's IL, then the magnitude of VL is omega L times the magnitude of IL, okay? Depending on omega L is smaller than or larger than 1, VL will be some, either will have a smaller magnitude or larger magnitude, and the ratio of the magnitudes will be depending on not only on inductance but also on the operating frequency, okay? And then how about the phase? Note that this thing, omega L IL, is multiplied by J, okay? Now, J is e to the J pi over 2. It can be written as such. And when you multiply something by e to the J theta, let's say, what happens is you don't touch the magnitude and then you rotate the thing that this is multiplying in counterclockwise direction by theta radians per second. Now, since we're multiplying this omega LIL thing by J, it means we're rotating it 90 degrees in counterclockwise direction. Therefore, the phase difference between voltage and current phasors of an inductor will be 90 degrees. Okay, so this is our VL. Okay, so for this situation, the current phasor IL is set to lag the voltage phasor. Phasor VL by 90 degrees. So lagging means it's coming behind, and why it's coming behind is just a way of looking at things, because to find the real time, the time domain signal, what we do is we multiply these things by e to the j omega t and then look at their real parts. And multiplying something by e to the j omega t produces rotation in counterclockwise direction with frequency omega radians per second. So in a sense, when multiplied by e to j omega t, this thing starts rotating, okay, in counterclockwise direction. And when that's the case, it appears as if the current is running behind the voltage, tries to catch it. That's why, because it's behind, it looks behind, of course everything is relative, the current is set to lag the voltage for this case by 90 degrees. Okay, let's talk about the capacitor also. We don't have to go much into the detail because it's a dual component, and what we expect is IC equals j omega c VC. Okay, replace the inductance by capacitance, voltage by current, and current by voltage. Okay, so for the capacitor, we have this plus minus VCT. This is ICT. As before, we assume that this capacitor belongs to an LTI circuit that's in sinusoidal steady state. That allows us to express the capacitor voltage and the capacitor current through their phasors. Okay, capital VC being the phasor of VCT, and likewise capital IC being the phasor of ICT, e to the j omega t. Once again, omega is the frequency of operation. Okay. So doing the same thing that we did to inductor, starting from the terminal equation, one can easily reach the following very nice algebraic equation satisfied by the current and voltage of the capacitor. So what we have is the phasor of the current equals some constant times the phasor of the voltage, and that's some constant which we will eventually call the admittance is j omega c for the capacitor. Okay, and as for the phasor diagram, real, imaginary, zero, suppose that this is the phasor of the voltage, Vc. Then Ic is, first of all, magnitude of Vc is scaled by a factor of omega c, and then as for the phase, it's multiplied by j, so the whole thing is multiplied by j. So that means we're rotating the voltage by 90 degrees, counterclockwise direction. So if this is Vc, we have to have Ic here, where the separation is 90 degrees. And for this case, this time voltage is running behind the current, and current this time leads the voltage by 90 degrees. Okay. Or you can say voltage lags the current by 90 degrees. Okay. Now, what we have discovered is quite remarkable. That is, even though the current and voltage satisfy a relation in time domain that's described by a differential equation, in phasor domain, or from the phasor point of view, the relation is purely algebraic. Okay, not for both capacitor and inductor. For resistor, it's automatically algebraic. It directly follows from Ohm's law. That for everything, every relation for our key players, RLC, become algebraic. Okay, and that motivates that motivates us to introduce the concept of generalized resistance, which we're going to call impedance, and it's defined as follows. Now, impedance, which is a new word, and it simply means resistance in a generalized setting. And likewise, we have the dual concept, admittance, which just simply means generalized conductance. Okay. Now, here is how it's defined. Consider a one-port, an LTI one-port that satisfies the following two conditions, is part of a circuit in sinusoidal steady state and contains no independent sources inside. Okay, and whenever there is a dependent source inside our one port, its control variable must also be inside the one port. Okay, contains control variables of of its dependent sources, if there are any dependent sources inside. Okay. Okay, so we have that for the following picture. Okay. So we have this one port here that's part of and circuit, LTI circuit in sinusoidal steady state. The one port contains no independent sources, and if there are dependent sources, all the control variables are also within this box. Now, let's directly express voltage and current in terms of their phasors. This is V and this is I. The phasor of the current associated with this one port and phasor of the voltage that appears across the terminals of our one port. Okay, I, V are the phasors. And for this one port, one can define the following. First, impedance. Impedance simply is generalized resistance, by which we mean the ratio of voltage phasor to the current phasor. Okay. Impedance is usually denoted by the letter Z, and it's the ratio of voltage phasor to current phasor. So it will have the following form: some magnitude and e to the j theta z, some phase theta, or sometimes in this form, the z. And just like resistance is measured in ohms, okay, in time domain, in phasor domain, we're going to measure impedance also in ohms, because we're taking the ratio of voltage to current. Likewise, the voltage phasors are measured in volts and current phasors are measured in amps. So we carry all the units directly to the so-called phasor domain, measured in ohms. Okay. Now, as for admittance, it's the dual definition. Simply, we're taking the ratio of current to voltage. And impedance is denoted usually by the letter Y. Y equals I over V, which clearly equals 1 over the impedance. And it's measured in mhos, okay, or Siemens. Okay. So, as we said, impedance is a generalization of resistance, and furthermore, its real and imaginary parts have certain names. Later on, we'll see the importance of the real and imaginary part of the impedance of one port from the power point of view. Okay. Impedance, as we said, is the generalization of resistance in phasor domain. Okay. Now, one thing that we have to be careful about is it is a function of the operating frequency. Omega. Okay. For instance, take the inductor. its impedance, according to this definition, we just figured out to equal what? J omega L. And as the frequency of operation changes, even though the inductance is constant, the ratio of voltage to current changes by omega. Okay, and likewise for the capacitor, and therefore likewise for this one port. Okay. Now, impedance Z can sometimes be, can always be expressed in rectangular form, and sometimes it's useful to express it in rectangular form. Okay, and when we do that, we write it as R plus JX. Okay, so by convention, usually the real part is denoted by R, and the imaginary part is denoted by X. And those real part and imaginary part, they have special names. R, which is the real part of the impedance of a one port, is called the resistance of the one port, and the imaginary part, X, is called the reactance of the one port. Okay. And as for the admittance, its real and imaginary parts have also special names. Okay, we write usually Y as G plus J B. G is the conductance of the one port, and B is the susceptance of the one port. So G equals the real part of the admittance, and it's called conductance. And B is the imaginary part, called susceptance. Okay. Now for LTI resistor, there's a relation between resistance and conductance. It's simply they're reciprocals of one another. But here we have to be careful. Okay. So let me put it as a warning here. In general, R is not 1 over G, or X is not equal to 1 over B. Okay. R in general not equals 1 over G, and X is not in general equal to 1 over B. Okay. In general. Okay, now let's apply this definition of impedance and admittance to what we have discovered regarding our components: resistor, capacitor, and inductor. So we have obtained the following component. Here is its impedance, and here is its admittance. Okay, for a component resistor whose resistance is R, the impedance, the ratio of voltage phasor to current phasor, equals the resistance. Okay, and admittance is simply 1 over R. Okay, it's purely real. As for an inductor whose inductance is L, the impedance, the ratio of the voltage to current for an inductor, is J omega L, and YL is 1 over J omega L. Okay. Now, unlike resistor, the impedance of an inductor depends on the frequency of operation. Different frequency would mean different impedance. As for the resistor, it's always the same, regardless of the frequency. And as for the dual component capacitor, whose capacitance is denoted by C, we have impedance equals 1 over J omega C, and admittance equals J omega C. Okay. Now, in phasor domain, therefore, any two-port under the assumptions that we listed can be represented by an impedance, by a constant, a complex constant, which indicates the ratio of voltage to current phasors. Okay. So since that holds, plus we know that KCL and KVL hold in phasor domain, that allows us to carry certain things that we're familiar with from LTI resistive circuits to the phasor domain. For instance, series and parallel connections. Okay, suppose that you have a bunch of one ports connected in series, and each one port, suppose, satisfies those assumptions and can be represented by its impedance. Okay, with this connection from Z1, Z2, Zn, from n one ports, we generate a new one port, and this one port again will have an impedance, and not surprisingly, the impedance of this new one port equals the sum of those n individual impedances. So this is called Z effective or Z equivalent, and since KCL, KVL hold in phasor domain, Z equivalent equals the sum of individual impedances. Z1 plus Z2 plus Zn. And the dual case also holds. Okay, we have a bunch of one ports, this time connected in parallel. And we construct this new one port, and it turns out that the admittance of this new one port equals the sum of individual admittances. Okay. In terms of impedances, let's call it Z1, Z2, Zn. We have 1 over Z equivalent, which is the equivalent impedance for this new one port, equals the sum of individual impedances. Zn. Okay. Now let's apply this to a simple example, an example one port, for which we will compute the impedance, equivalent impedance. Consider this one port that contains 3 individual components. Here we have an LTI inductor, a resistor, and a 1 farad capacitor. And this is part of a circuit that's in sinusoidal steady state, and the frequency of operations. Now, frequency of operation for that circuit is 2 radians per second. So what we're asked is find Z for omega equals 2 radians per second. Note that we have to have omega information. Otherwise, we cannot figure out Z, because Z is a function of omega, unless your one port contains only resistors, LTI resistors. Okay, so here is the solution. What we're going to do is we're going to replace each of these components with its impedance. Okay, and then once we have those impedances, these two impedances are in parallel, we can figure out the equivalent impedance, and then that impedance will be in series with the impedance of the inductor, and by series connection identity we can easily obtain the overall input impedance, effective impedance for the one port. Okay, so in terms of their impedances, let's redraw the circuit. The impedance of the inductor equals j omega L. Omega is 2, L is 1 over 2, and what we have is j times 2 times 1/2, which is j times 1, or j. Now the remarkable thing here is this Henry becomes ohms. Okay? In other words, the differential equation becomes an algebraic equation from the voltage current point of view. So that's the remarkable thing about working with phasors. Likewise, the impedance directly equals the resistance. It's independent of the frequency, so we just copy whatever we see here 1 over 3 ohms. And as for the capacitor, the impedance is 1 over j omega C. Okay, C is 1, omega is 2, so what we have is 1 over j2. That j we can carry upstairs and write minus j 1 over 2. The units, here we have farads, here we have ohms. Okay, differential equation, algebraic equation. Note that we have 3 different units here, Henry, ohm, farads, but now everything is in ohms. Okay, so everything is represented by an algebraic equation, which allows us indirectly to be able to talk about an equivalent impedance. Okay. Okay, so this is equivalent to the following. Okay, so this is equivalent to what? First, let's combine the capacitor and the resistor. And we have this single one port representing this combination of resistor with the capacitor. And the impedance of that one port is 1 over 3 ohms combined in parallel with minus j 1/2, and that's 1 over 3 plus j2. Okay, and written in rectangular form, this reads 3 over 13 minus j2 over 13 units is ohms. And here we have the impedance of the inductor, which is j ohms. And finally, the equivalent impedance for this guy and that guy connected in series is simply you add j with that impedance, and this is what you have. J in series with 3 over 13 minus j2 over 13, and that equals 3 over 13 plus j11 over 13 ohms. Therefore, the impedance of this one port equals this number when when the frequency of operation is 2 radians per second. You change the frequency, this changes, okay, because the impedances of capacitor and inductor changes with respect to the frequency. Okay. Now, we have seen that KCL and KVL hold in phasor domain. We have seen that resistor, inductor, and capacitor behave from the phasor point of view like generalized resistors. Okay, therefore they're all represented by an algebraic equation, just like the Ohm's law. Okay, and combining those two sets of findings, we will be able to easily analyze circuits, LTI circuits in sinusoidal steady state. Okay, and we are almost ready to start our developing our theory, to start our analysis of such circuits. But we have still a few other components that we haven't talked about yet. So let's quickly see what they become from the phasor point of view. I'm talking about the components like independent sources, dependent sources, coupled inductors, and the ideal transformer. And then once we easily obtain the phasor, the relationships, the terminal equations from the phasor point of view, we will be ready to start our phasor domain analysis of LTI circuits. Okay, so let's see how an independent source can be represented through its phasor. And then we will move on to dependent source and coupled inductor and ideal transformer. Okay. Independent sources. For circuits in sinusoidal steady state. Okay, so suppose that this is our independent voltage source, and since we're talking about the case SSS, this must necessarily be a sinusoidal function. Vm, suppose it indicates the magnitude, then we have cosine omega t plus some phase, phi b. In phasor domain, okay, all we have to do is to represent this in phasor domain, we have to transform its time domain, the voltage that it produces, to its phasor domain equivalent. So, and when we start eventually drawing phasor domain circuits, we will just draw the same thing from the picture point of view, and instead of putting Vs of t here, we will have capital V of S, and this is the phasor of the sinusoidal signal. Okay, Vs equals the magnitude and phase. And this simply means, well, this is same as this, okay, Vm e to the j phi v, the phasor of Vst. Okay, so in time domain, Vs of t is the sinusoidal function, therefore its value changes with respect to time, but in phasor domain, it behaves like a DC source. Its value is fixed at some complex number, which we call the phasor of Vs of t. And same goes for the current source. Ist equals some magnitude cosine omega t plus some phase. And in phasor domain, this component can be represented by a constant, and that constant is the phasor of this signal here. Capital Is, which is Im phi I. Okay, so there's nothing much interesting regarding independent sources. How about dependent sources? Suppose that we have a current control voltage source, okay? It's our dependent source, and in time domain, the relation between the voltage and its control variable, which is current, is this algebraic relation. V equals some constant times Ix of t, and Ix is the control variable of this dependent source, some current somewhere in the circuit. And then in phasor domain, or from the phasor point of view, it directly follows from the definition that the phasor of this voltage equals this constant mu times the phasor of the control current. It's just like the LTI resistor that we have studied recently. So in phasor domain, the terminal equation directly is carried in same form. Here we have the phasor of the voltage, capital V. It's a function of time. This is constant. And we have V equals mu Ix. This is phasor of V of t. And this is phasor of the control current, Ix of t. So in particular, whenever you have an algebraic equation in time domain, like the resistor or the dependent source or ideal transformer, the equation directly carries into the phasor domain without any alteration. Okay, how about the coupled inductor? L1, L2 self-inductances and the mutual inductance I1 and I2 are the currents of the coils. Okay, and then in time domain we know that V1, V2 equals L times di. L is our inductance matrix, L1, M, L2, and then we have d times the current vector, or in other words, we have the I1 and the I2. And then in phasor domain, or from the phasor point of view, the relations between the voltages and currents become the following. And the derivation is almost the same as the derivation for a single uncoupled inductor. So whenever we start eventually drawing circuits in phasor domain, we just draw the components as the same. Okay. Here we have, instead of the time domain signals, we have their phasors. V1, V2 are the voltages. Here we have I1. Here we have I2, the phasors of the currents. Now, as for inductances, self-inductance and mutual inductance, we replace them by impedances and, well, in a sense, mutual impedance. Okay, so what we mean by that is, instead of L1, here we have j omega L1. Omega is the frequency of operation of the circuit, which this coupled inductor is part of. Here we have j omega L2, and here we have j omega n. And now the question is, what does this picture tell us? It tells us the following. V1, V2 equals some constant matrix times I1, I2. Okay, so here we have a differential equation in matrix form, and that equation becomes an algebraic equation in phasor domain. The voltage vector equals some constant matrix times the current vector. And now what are the entries of this constant vector, or the impedance constant matrix, or the impedance matrix? Well, all you have to do is multiply this matrix by j omega, or we have j omega L1, j omega m, j omega m, and j omega L2. Okay, so this means, therefore, that this picture means phasor of V1 equals j omega L1 times I1 plus j omega m times the phasor of the second current. And likewise, phasor of second coil's voltage equals j omega L2 times I2 plus j omega m times I1, okay, which is expressed in this matrix equation. And finally, the ideal transformer. Since the terminal equation for the ideal transformer is algebraic in time domain, what we do is we just write down the same equation in phasor domain, the only difference being that instead of time domain signals, we now have capital letters representing the phasors. Okay, so ideal transformer turns ratio N1 to N2. Okay, so let's denote V1, I1, I2, and V2, the voltages and currents, okay, of the first and second coils, and the terminal equations are such that V1 over N1 equals V2 over N2, and as for the currents, N1 I1 plus N2 I2 equals 0. And in phasor domain, not surprisingly, all you have to do is rewrite the same equations only by capitalizing the V's and I's. Okay, phasor domain. Now let me draw the exact same figure for the sake of completeness. Plus minus. Now we have capital V1. Now we have here capital V2. This is capital I1. This is capital I2. These are time domain signals, also sinusoidal functions oscillating at some frequency omega, and here we have constants V1, V2, I1, I2. Okay, and as for the equations, V1 over N1 equals V2 over N2. The same equation here, only the voltages are capitalized, and finally N1 I1 plus N2 I2 must equal 0. And now our list of terminal equations for an LTI circuit components is complete. So we have the terminal equations from the phasor point of view. We have figured out that KCL and KVL hold for the phasors of currents and voltages respectively. Therefore, that means we have everything we need to start developing analysis techniques to study LTI circuits in sinusoidal steady state. This we do in our next lecture.